Welcome to Spaceverse, your portal to cosmic adventures. Far beyond the bright glare of familiar stars, tucked away in the dark and cold corners of our galaxy, astronomers have stumbled upon something extraordinary. Using NASA's cutting-edge James Webb Space Telescope, researchers have uncovered the most chemically rich disk ever observed around a brown dwarf, a cool, faint celestial object often described as a failed star. And this discovery is shaking up our understanding of how worlds are born. This cosmic laboratory is called JWST Alpha 1. It's a young brown dwarf, barely a fraction of our sun's mass, wrapped in a swirling, luminous cocoon of gas and dust. Within this disk, planets might someday form, and what Webb has seen there is astonishing. To appreciate why this matters, it helps to understand what a brown dwarf actually is. Brown dwarfs occupy a strange twilight zone between stars and planets. They form the way stars do, by collapsing clouds of gas, but they never get massive enough to ignite steady hydrogen fusion in their cores, the defining trait of true stars. Because of this, they glow faintly, emitting mostly infrared light, and they fade slowly over time. They're sometimes called failed stars, but that name undersells their importance. In fact, brown dwarfs are invaluable to astronomers because they offer natural laboratories for studying the earliest stages of planet formation, stripped of the intense heat and radiation that larger stars produce. Around many stars, we see disks of dust and gas where planets are gradually assembling, but the disks surrounding brown dwarfs are different. They're cooler, thinner, and quieter, and that matters because the temperature, pressure, and turbulence inside a disk control how its material behaves. In these calmer environments, water-rich icy grains can drift inward quickly and be swallowed by the brown dwarf, while lighter carbon-rich particles are less likely to be dragged inward and can linger, building up over time. The slow pace and gentle conditions mean that distinct chemical zones within the disk can survive much longer than they do around hotter, more energetic stars like our Sun. As Camber Schwartz, a postdoctoral researcher at the Max Planck Institute for Astronomy, put it, in the disks around low-mass stars and brown dwarfs, water-rich dust grains move quickly and are accreted by the star, leaving behind the more carbon-rich dust. And that has huge implications, because planets born from such material could end up chemically very different from Earth or other worlds orbiting Sun-like stars. This is what makes Webb's new observations of JWST Alpha 1 so thrilling. In August 2022, astronomers used Webb's mid-infrared instrument, known as MIRI, to study the young brown dwarf, and what they saw astonished them. JWST Alpha 1's disk is overflowing with molecules, hydrocarbons like methane, acetylene, ethane, and even benzene, along with water, carbon dioxide, hydrogen gas, and large silicate dust grains. It is, quite simply, the richest mix of planet-building chemicals ever recorded around a brown dwarf. This discovery didn't appear out of nowhere. Nearly 2 decades ago, NASA's now-retired Spitzer Space Telescope studied the same object. Even with its far blurrier vision, Spitzer hinted that the disk was unusually complex. But now Webb, with its razor-sharp infrared eyes, has confirmed those suspicions in dazzling detail. And that confirmation matters because it means this chemistry isn't just a temporary flare-up or an observational trick, it's a persistent feature of the disk itself, something stable and enduring. Thomas Henning, a senior scientist at the Max Planck Institute, says these findings provide a rare, detailed look at how planet-forming chemistry operates under extreme conditions, and that could help explain the stunning diversity of exoplanets we see across the galaxy today. But there's something even stranger. Typically, disks around young stars tend to lean one way or the other. If they're oxygen-rich, they produce lots of water and silicates, while if they're carbon-rich, they favor hydrocarbons, molecules built from carbon and hydrogen atoms. Seeing both oxygen-bearing and carbon-rich molecules at once side by side is incredibly unusual. Schwartz explains, carbon loves bonding with oxygen. The fact that we don't see any oxygen in these hydrocarbons tells us they formed in a very oxygen-poor region of the disk, different from the region the water and carbon dioxide is coming from. In other words, the disk is like a chemical patchwork quilt. Different regions have very different environments. That level of chemical diversity suggests JWST Alpha 1's disk is quite young. Over time, mixing usually erases these differences, so catching it now is like peering back in time to see the very first steps of planet formation as they unfold. And the surprises don't stop there. Webb's MIRI data also revealed evidence of large silicate dust grains floating in the upper layers of the inner disk. That's significant because in space, dust grains are the raw seeds from which planets grow. As Thomas Henning explains, dust creates a solid surface in space, which is essential to form complex molecules. Large dust grains don't exist in the interstellar medium, but are important for planet formation. Having dust grains in a range of sizes allows giant planet cores to grow much more quickly than if all the dust was the same size. In other words, the fact that large dust grains already exist in this young disk suggests planet formation could start sooner and proceed faster than expected. And it's not just the size of the grains, it's also what molecules are present. Many simple molecules like carbon dioxide and hydroxide are missing, while more complex molecules have already appeared, meaning this disk is already well along the road of chemical evolution despite its youth. This discovery opens a rare window into how chemistry sculpts the birth of planets. Every planetary system, including our own, was shaped by the specific mix of elements and molecules present in its natal disk. If a disk is rich in water and oxygen, it may produce rocky, Earth-like worlds with oceans, while if it's carbon-heavy, it could spawn exotic planets made of carbides, graphite, or even diamond-like material deep within their interiors. JWST-1's disk seems to be offering both ingredients at once, and that's profoundly intriguing because it could hint at entirely new kinds of planets, worlds unlike anything we've imagined. Imagine a system with carbon-dominated inner planets, perhaps with black, glassy crusts, and oxygen-rich outer planets shimmering with icy oceans. This isn't science fiction, it's a possible outcome written in the chemistry Webb has revealed. But this story is far from over. Webb has shown us what's inside the disk, but not how those ingredients are distributed or how they interact. As Henning notes, we've only been able to characterize the gas properties and dust properties separately. We need to look more at how the dust and gas interact with each other. That's critical because the interaction between dust and gas drives the entire process of planet formation, how dust clumps together, how it migrates inward or outward, how it grows from grains to pebbles to planetesimals to full planets. And nestled within Webb's data are mysterious spectral fingerprints, features that don't match any known molecules studied on Earth. These could be entirely new molecules, never seen before, forged in the unique chemistry of this young disk. And if confirmed, they would expand our catalog of cosmic chemistry and perhaps reveal new building blocks for life or planetary formation. This is the power of the James Webb Space Telescope. It's not just showing us distant galaxies and ancient starlight, it's revealing the hidden details of nearby worlds in the making. It's telling us what ingredients go into the cosmic recipe book, and how those ingredients get stirred, baked, and shaped into planets. And JWST-1 is now one of the most fascinating case studies in that story. A small, faint brown dwarf with an unexpectedly rich, vibrant chemical nursery swirling around it. A place where worlds might be born. A place that reminds us that even the universe is quiet, overlooked corners can be full of wonder. So what does this mean for the bigger picture? It means that planet formation may be more flexible and widespread than we thought. If a tiny, low-mass brown dwarf can build up such a rich chemical environment, then the galaxy might be teeming with small planetary systems around faint stars and brown dwarfs, systems that have gone unnoticed until now. And that, in turn, expands the possible habitats for life. It suggests that life-friendly chemistry might spark not only around sun-like stars, but around far dimmer and cooler objects as well, meaning billions of hidden, tiny solar systems might be quietly assembling across the galaxy, waiting to be found. And this is only the beginning. Webb will continue to survey disks around young stars and brown dwarfs, building a library of snapshots at different stages of their evolution. By comparing these disks, young and old, hot and cold, simple and complex, astronomers can piece together a grand timeline of how planets are made. Step by step, molecule by molecule, they're reconstructing the recipe for building worlds, and JWST-1 is now a key piece of that cosmic puzzle. The universe still holds countless secrets, and every new discovery reminds us how much more there is to learn. Change Alpha 1 shows us that even the smallest, dimmest objects can nurture the raw materials of worlds and maybe, someday, life. Who knows what other hidden wonders the James Webb Space Telescope will reveal next? Thanks for joining us on this journey through the cosmos. If you enjoyed exploring the mysteries of space with us, be sure to subscribe to Spaceverse and turn on notifications so you never miss a new voyage into the stars. Until next time, keep looking up because the universe is just getting started.